Hi everyone. If we knew future, we would know which object to cache and which not. Well, of course, we don't know future. In this work, we use machine learning that mimic what if we know the future and what we would do. And we show that it dramatically improves the caching performance. Let me first introduce CDN. CDN put edge cache near users. If users' request hit the cache, the content directly returned to the user. If the request doesn't hit the cache must fetch the request from wide area network, or WAN. WAN traffic is expensive, and CDN seek to minimize it. The key metric here is byte-miss ratio, which is the ratio of bytes that miss in a cache to the total byte it serves. Caching is a challenging topic. For more than 5 decades, people studying it, many caching algorithms has been proposed, and most of these algorithms are heuristic-based algorithms. This algorithm works well for some workload, but poorly for others. Recently, there have been several proposals that use machine learning to adapt heuristic. Unfortunately, this approach suffers from the similar limitation. They work well on some workloads, but poorly on others. Compared to the Belady MIN algorithm, which is an oracle algorithm assuming future knowledge, we still observe a large gap in production traces from 20 to 40%. And to build this gap, our algorithm, Learning Relaxed Belady, takes a fundamental different approach. It does not build on heuristic. It does not trying to optimize heuristic. Our algorithm is mimicking a new variant of Belady's algorithm using machine learning. Here is a general overview of our approach. In addition to serve current requests, the system stores information about past requests. With this information, it generates training data. And then the training data is fed into a machine learning architecture that trains a model. Then, when the cache is full, it needs to do eviction. It first selects eviction candidates and query the model to determine which object to evict. Turning this overview to a practical system, however, requires us to solve 5 key challenges. First, what past information to use? More information can improve the model quality, but use up the memory that could otherwise be used for caching object. Second, how to get online training data. Similar to the Zhenyu people which presented earlier, we don't want to train the model offline and evaluate them online. That's why we want the model to be trained online and quickly adapt to the workload change over time. Third, what machine learning architecture to select from a very large design space, including features, models, prediction target, and the loss function. And fourth, how to select eviction candidate in order to keep a balance between the low byte-miss ratio and low computation overhead. Solving each of the previous challenge is hard because there is a large design space, and it takes a long time to evaluate a new design decision. End-to-end simulation of byte-miss ratio on our trace takes 2 days. Thus, our final challenge is find some way to quickly evaluate our design decisions. To solve this challenge, we introduce the Relaxed Belady algorithm and the good decision ratio metric, and which is built on top of Relaxed Belady. We first use good decision ratio to speed up the evaluation design decision process from days to minutes. And then we use both Relaxed Belady and good decision ratio to solve the first 4 challenges. Next, I'm going to motivate and introduce Relaxed Belady. Belady is an oracle algorithm, meaning it assumes future knowledge. And its eviction policy is pretty simple. just evict the object whose next access farthest in the future. Here is a demonstration that a cache required to do an eviction. The x-axis shows time to next request for all the objects in the cache. And Belady will evict object C because C is the furthest. However, we find that mimicking exactly Belady is difficult. There are two reasons. One, to find the object with access furthest in the future, we need to run predictions for all objects. And this happens on every eviction. This will introduce a prohibitive computation cost. Second, to find the furthest object, we need exactly prediction of next access. However, in practical, we found that predictions are inaccurate. And what worse is that the furthest prediction are the most inaccurate. To solve this challenge, we introduce the Relaxed Belady algorithm. Our key insight is that many objects are good candidates for eviction. To give you an example, let's see the most far object A and C. Suppose A will be accessed again in a year, and C will be accessed again in 2 years. Both objects are similar for eviction now because neither of them will likely to receive another hit before exactly Belady would evict them for the cache. To capture this similarity, we introduce the Belady boundary and treat all the objects beyond the boundary whose nexus beyond the boundary the same. And the boundary is chosen by offline analysis, which you can find in our paper. To be more precise, what Relaxed Belady does is it randomly samples objects whose next access beyond the boundary and use that for eviction. And we found that Relaxed Belady has a similar bad-miss ratio to exactly Belady. Specifically, Relaxed Belady enables a practical system design for two reasons. First, it does not require predictions for all objects. We need only find the one object that beyond the boundary, which is possible with reasonable computation cost. Second, it does not differentiate between objects beyond the boundary, and this greatly simplifies our prediction task because our predictions do not need to be so far. And next, based on Relaxed Belady, we introduce a new metric, the good decision ratio, that allows us to evaluate design decision quickly. And to end miss ratio is what we care about, but that is slow. And our key insight is that Relaxed Belady gave us a way to evaluate individual eviction decision. To give a demonstration, we treat an eviction decision as bad if the evicted object's next access is within the boundary, as the Relaxed Belady would have not evicted that object. And we say the eviction decision is good if the evicted object access is beyond the boundary, as the Relaxed Belady would evict that object. And the good decision ratio is thus the number of good eviction decisions by the number of eviction decisions in total. Next, I'm going to show how we use this to evaluate our system design in a quick way. Remember, the question is the end-to-end simulation takes a long time. And our solution is to use good decision ratio to evaluate many design decisions without rerun the complete simulation. To do that, we first log the training data and eviction candidates during one simulation, and then we use them to evaluate many designs. The good decision ratio allows us to meaningfully evaluate the quality of our design decisions using this lightweight process. With that, we can now evaluate designs in minutes instead of days. And just to be clear, this is only used in our design process, not a component of our final system. Next, let's see how we solve this first challenge. The question is what and how much past information to use to have a better trade-off between the amount of data and the space overhead. We design a sliding memory window which mimic the Belady boundary in Relaxed Belady. And we only track objects in this sliding memory window by storing per object features for them. Once an object passes this memory window, LRB deletes its features. Such an object would have been evicted by Relaxed Belady long time ago, so it's not worth to track that. And the memory window size is LRB's main hyperparameter. Next, let's see how to generate online training data. We get training data by randomly sample from the object within the memory window and record their features. Because our target is predicts the time to access for this object, the training data right now is incomplete as we don't know the correct label yet. We later complete this training data either when the object is accessed again, and thus we know the correct label, or when the object is past the memory window. Such object would have been treated equivalently by Relaxed Belady, and so we treat them equivalently by giving them the same label. We use a small training batch to be able to do fast training. Next challenge is how do we select the machine learning architecture that can make good decisions with low cost. And the space includes features, models, training batch size, prediction target, loss function, but I will only briefly cover our feature and models. We use good decision ratio to evaluate different designs, and the features we select are the object size, type, because they classify object into different classes, and we also track inter-request distance as a recency feature, and track the exponential decay counters, which track the long-term frequencies. And the model we select is gradient boosting decision trees, as it is lightweight and achieve high good decision ratios across all the trees. With this selection, we are able to finish training within 300 milliseconds, and this allows us to make predictions for a batch within 30 microseconds, which translates to 30K per second. Next, how we select eviction candidates. Our solution is we randomly sample K candidates from the cache. And we show that a small sample is sufficient to mimic Relaxed Belady because we only need to find the one object beyond the Belady boundary. And we sample 64 candidates because more does not improve the good decision ratio. OK, so by combining all this design, we have our algorithm LRB that mimic Relaxed Belady. The cache track past object within the memory window, and periodically sample object to generate unlabeled training data set. After the object is accessed again or past the memory window, we label the corresponding training data. And when we calculating a new batch of training data, and when that is full, a new model is trained. And when the cache need to do an eviction, it first samples 64 candidates, and then use the model to predict their time to next access and evict the furthest one. And this process continues over time as new requests come in. LRB generates new training data and trains a new model so it can quickly adapt to change in a workload. OK, so we implement LRB in both a simulator, which has LRB and 14 other algorithms. We also implement a prototype using C++ on top of production server, Apache Traffic Server. And we also apply many optimizations to make it fast. Next, our evaluation of LRB asks two major questions. First, as our goal is one traffic reduction, what is LRB's traffic reduction compared to the state-of-the-art algorithm? Second, to ensure the system is practical, what is the overhead of LRB compared to CDN production system? To evaluate this question, we use 6 production traces from 3 CDNs. And to prevent overfitting, we tune all our hyperparameters on the first 20% of the trees and only evaluate them, the algorithm on the rest of the trees. OK, first, let's look at the result at the Wikipedia trees. The y-axis shows traffic reduction compared to BRU, which is an industry standard algorithm. And the x-axis shows different cache size ranging from 64 GB to 1 TB. In addition to the BRU baseline, we also show the top algorithm from our 14 tested algorithm. And our algorithm, LRB, it achieves 20% traffic reduction over industry standard of art and 10% over the state-of-art algorithm. In addition to Wikipedia trace, we also test LRB on the other 5 traces from the other 2 CDNs. Here are the results from 2 traces of CDN A, and LRB reduced 1 traffic over industry standard and state-of-art algorithm. We see similar results in 3 traces from CDN B. By looking at this trace together, we found except LRB, no other algorithm is robust at all traces. And note that even in the large cache size, the 4 TB, for example, the improvement is still huge. Let me briefly touch on the overhead of LRB. In terms of throughput, LRB achieved 11.7 Gbps throughput, which is very close to unmodified system. And its peak CPU usage is 16%, with 9% compared with the unmodified system. While this is higher, but it's well within what is available on the CDN machine today. And LRB used 1 to 3% of cache size as the overhead to track the metadata. This small memory overhead has a small effort on the capacity, which all our experiments account for. To conclude, we designed Learning Relaxed Belady. It consistently reduced 1 traffic compared to the industry standard of art and the other state-of-art algorithm. And it also has a modest implementation overhead. Our design is driven by the key insight of Relaxed Belady algorithm. It simplifies the machine learning requirements and reduces the system overhead. And based on it, the good decision ratio enables us to evaluate new design decisions in minutes, which also allow fast design iterations. And finally, our code and trace are available online. Please check that. And I would be happy to take questions or discuss with you offline. Thank you.
Any questions? So while people are getting up, I have a question. So you decide to relax and sort of have this boundary. Or,
right.
OK, after that boundary, it's not good. So I'm wondering, because don't you have boundary effects, like things that should be cached might be close to that belayed boundary, and it's hard to decide there. Like if you had something that's more continuous,
right.
Perhaps you could have a more precise prediction?
Right. The reason, I think the question is whether we want to predict a continuous value or the binary value.
Yeah.
The reason we use binary value is actually simplify our machine learning, although there is like limitation you previously mentioned. And also, based on the binary prediction, we can have the good decision ratio, which allow us to do quicker design evaluations. Thank you.
Thank you for the nice talk. Ymir Vikvason, Emory University. I'm wondering if you could bring any lessons back from this black box machine learner back into like, what are the heuristics that we should be doing? Did you look at any surrogate models or something for understanding what your black box is doing, like Lime and things like that? Right. Or like, is there a particular feature, for instance, that seems to be dictating the performance benefits that you're seeing, like size?
Right. OK, so the question is by looking at the model, any heuristic we can learn from the model. We actually check the importance of all the features. And a little bit slightly, like on all the traces, the feature importance are different. So which means it's very hard to design the heuristic on all the traces. And this could be also like why people have spending more than 5 decades, but still don't get a good heuristic algorithm.
Awesome.
OK, thanks. Let's thank all the speakers. Oh, there's another question. Sorry. OK, you have a good.
Another question.
Another question. OK.
This is just
Announcement.
if you're speaking after lunch, please come up before lunch so that we make sure everything works.
Yes. So I'd like to thank all the speakers in particular because, as you've seen, everybody has put their codes available. We have all this data available. I really encourage people to do that so that we can have reproducible research. It's great to see that happening, all the papers in this session. So let's thank all of them. Thank you.